the past, but I'm going to give you guys a little baby review because we're going to be working with lots of probabilities. We won't be working with probability theory so much, but we'll be using discrete distributions and continuous distributions of variables to solve for probabilities. We'll be using tables in the back of the book, normalized variables to make probability statements. You'll see that it's really, really easy, but before we do that, we have to review probability. Again, it'll only take a few minutes, and then we'll move right into more sophisticated statistics. All right, the concept of probability is employed in describing populations and in using sample information to make statistical inferences. So let's review a few terms. First, experiment. So what is an experiment? We can define an experiment as any process of observation that has an uncertain outcome. So a process with an uncertain outcome. So any process of observation that has an uncertain outcome. An example would be drawing a card from a deck of cards or flipping a coin. So the flipping of the coin is the experiment. The rolling of the die is the experiment. If I ask you to pick a number 1 to 100, that's an experiment. It's a process and the outcome is uncertain. Next, what is an event? An event is simply an experimental outcome that may or may not take place. So it's an experimental outcome that may or may not take place. That may or may not take place. Again, an experimental outcome, an event is an experimental outcome that may or may not take place. Next, what is a probability? It is a number that measures the chance that the event will occur when the experiment is performed. So it's the chance that the event will occur. So the chance that the event will occur when the experiment is performed. So a probability is just a chance, the number between 0 and 1. For all practical purposes, the probability of an event is simply the proportion of time the event would occur if the experiment were performed a large number of times. So for example, the experiment of flipping a coin, what's the proportion of time that heads will occur if I perform that experiment, the experiment of flipping a coin 100 times or 1,000 times? Obviously that proportion is about 50%. So that's all a probability is. So if A is an event that may or may not occur when the experiment is performed, so an event that may or may not occur when an experiment is performed, then the probability that the event A will occur is denoted as PA. So this is notation that you'll see in stats or quant-oriented courses. So PA, if A is an event that may or may not occur when an experiment is performed, then the probability that the event A will occur is denoted PA. So PA is just the probability that the event A will occur. So if the experiment is performed, say, n exp times, and the event A occurs n a times, so we might perform the experiment of flipping a coin 100 times. And let's say the event of heads occurs 50 times, then NA divided by the number of times that we perform the experiment is equal to the probability of heads. In this case, it would be 0.50 or 50%. That the number of times that we repeat the experiment approaches infinity, the limit of the sequence of numbers obtained by calculating the ratio n sub a divided by n sub exp after each repetition is the probability of a, the probability of that event occurring. So mathematically what we're saying is that the probability of a is equal to the limit as the number of experimental trials approaches infinity, n a divided by n exp. So again, this is, a more technical definition of a probability. So the question is, or a little example, what is the probability of heads, or the probability of that event, for the experiment of flipping a coin an infinite number of times? So as we let the number of trials in the experiment increase to infinity, or as n sub exp increases to infinity, we flip that coin over and over and over. As we approach infinity, the ratio of n sub a to the number of trials, n sub exp, will equal 0.5. But again, I want to go back to the definition of a probability that you should sort of reference. When you think about a probability, just think of simply the proportion of time some event occurs if some experiment is performed a very large number of times. And we know that the probability has to be less than 1 but greater than 0. And we'll spend a lot of time working with probabilities in this class. We won't be working with probability theory so much, which is probably something that you discussed in your introductory statistics class while you were an undergraduate student, but we'll use continuous probability distributions to make probability statements. So let's say this is the distribution of some variable, some random variable. So if we know how this variable is distributed, and in this case it's a normal distribution, and if we normalize the variable so that the mean is equal to 0, so that we're looking at standard deviations from the mean, and again, this will all make more sense later. But if I ask a question, what is the probability of observing a value greater than 0? So what is the probability of observing a value greater than 0? Well, we know that the area under the curve is 100%, and in this case, that probability would be 0.5. We might inquire about the probability of observing a value of this variable that is in between -1 and +1 standard deviations from the mean. And again, we just solve for the area under the curve. We can do that using tables, or we can do that using Excel or statistical processing software like Stata, and easily obtain those probabilities. Okay, so moving on to random samples and sample statistics, we know that the calculation of population parameters, for example, solving for the population mean, requires knowledge of all the values in the population. If we don't know all the values, we must obtain a sample of n values from the population. So let's say the population has 1 million individuals. Let's say we're talking about college students or graduate students in Masters of Science programs. If that population contains 1 million students, we might select a random sample of 1,000 students. So a random sample of n elements, in this case 1,000 students, can be obtained if each student or each element has the same probability or chance of being selected in the sample. If we randomly select a sample of n elements, or students in this case, the values of the numerical characteristic of interest, we were talking about grade point averages from before, so the values of the grade point averages possessed by these students make up a randomly selected sample of n values. So for I from 1 to 2 to n, we let y sub I denote the value of the numerical characteristic under study possessed by the ith randomly selected element. So the set of y1, y2, all the way through yn. And we sometimes think of y as the dependent variable. Don't. In this case, y is just some variable. In our example, y is grade point averages. So if we have a sample of 1,000 GPAs, we'd have GPA 1, GPA 2, all the way through GPA 1,000. And that is our set of data. So this is our randomly selected sample of 1,000 students. The set of G1 to G1000 is the randomly selected sample of 1,000 numerical values. So what is a sample statistic? Moving right along, what is a sample statistic? So what is a sample statistic? A sample statistic, it's just a descriptive measure of a randomly selected sample of numerical values, some sort of descriptive measure. We could use sample statistics as point estimates, or estimates that are single numerical values of population parameters. So if the population under analysis contains 1 million students, I generate a random sample of 1,000 students. We can use this sample to solve for sample statistics. It's just a descriptive measure of the randomly selected sample of numerical values. So what sort of descriptive measure? Well, we can solve for the mean, we can solve for the variance, we can solve for the standard deviation. There are all sorts of sample statistics that we can solve for. And again, we use these random samples to solve for sample statistics. And we use these sample statistics as point estimates, or estimates that are single numerical values of population parameters. So although I don't know the population grade point average, I can take a random sample from the population and solve for the sample. So suppose that the sample is y1, y2, all the way through y sub n. And this is a randomly selected sample from a population. How do we solve for the average grade point average, or the average y? Well, in this case, you would just take the values of the individual elements from I is equal to 1 to n, and it's the number of students. We would take each student's grade point average and just divide that by n. So that's just the sample mean. How about the variance? The sample variance is often denoted S squared. It's a measure of variability. It's simply the sum of the squared deviations. So I is equal 1 to n y sub I minus y bar squared, all divided by n minus 1. In the numerator, we have the numbers of degrees of freedom. And since we're using this sample to solve for the mean, we have one less piece of information. So the number of degrees of freedom is reduced by 1. So the total number in the sample less 1. So if I look at a set of data, and if I know what the mean is, then I don't need one of the y values. I can solve for the last y value with all of the other y values and the mean if I know what the sample size is Anyways, just know that the degrees of freedom, when you work with a sample, you don't divide by n. You don't take the average of the sum of the square deviations. You take something close to the average of the sum of the square deviations. You divide by n minus 1. This is a point estimate of the true variance. The mean is a point estimate of the true mean. And if I take the square root of the variance, I get the standard deviation, which is an estimate of the population standard deviation, often denoted as sigma. We can solve for all of these values using Excel. I'm tempted to give you some numbers and ask you to solve for the mean, the variance, and the standard deviation, but I'm trusting that you can do that. If you haven't performed those calculations in a while, well, actually, we can just do like a weird baby example. Let's say we've got 3 values. So n is equal to 3. What is the mean? This might be some characteristic that we're interested in studying, but this is a random variable. There are 3 values. The values are 2, 4, and 6. So how do we solve for the mean? So y bar would be the sum I is equal to 1 to 3. Y sub I, and then all of that divided by 3. So 2 plus 4 plus 6 divided by 3, which is equal to 4. So y bar is equal to 4. Well, what about the variance? So the variance is the sum of the square deviations divided by n minus 1. So I'll do this just maybe once or twice, but I'm not going to spend a lot of time doing this sort of math. We can solve for these things very easily by hand. I know that this is way too fundamental, but we've got I is equal to 1 to n s sub I minus, y sub I minus y bar squared, all divided by n minus 1. So that's going to equal, well, the average is 4, so y bar is 4, so y sub 1 is 2. So 2 minus 4 squared plus, so you just perform this mathematical process, take a difference and square it for each I, for each student, or for each observation. So 4 minus 4 squared plus 6 minus 4 squared, and we divide that by n minus 1, or 3 minus 1, which is 2. So negative 2 squared is 4, plus 0 plus 4 is 8, divided by 2, which is equal to 4. So that is the variance, and I can take the square root of the variance to get the standard deviation. So in this case, the standard deviation is 2. So this is the cool thing. If you know the variance, or if you know the standard deviation, and if you know the true population average, and if you know the standard deviation, you can normalize these values and make all sorts of probabilistic statements if we know how this variable is just shifted. So we'll get to that in a little bit, but those are just some baby examples of how you perform those calculations by hand. So let's move on to continuous probability distributions. So continuous probability distributions. So continuous probability distributions, and I know I'm going fast, and I can give you notes packets to supplement this discussion, and you're probably following along. So before we randomly select a value y from a population, y potentially can be any of the values in the population. So let's say that we've got 1 million students, and I randomly select 1 student and get their grade point average. That grade point average can be something between 0 and 4. It can be one of the population values. So we can use continuous probability distributions to calculate probabilities concerning y, the value that y might attain. So again, we can use continuous probability distributions to calculate probabilities concerning the value y might obtain. So again, if I'm just randomly selecting somebody from the population, y potentially can be any of the values in the population, so I can use the continuous probability distribution to calculate probabilities concerning the value y might obtain. This sort of implies that I know the probability distribution, so we'll see some examples in just a minute. But for now, consider the closed interval from A to B on the real number line. So we're going to denote this interval as follows: A to B. We often wish to find the probability that y will be in the interval A to B. We often wish to solve for this particular probability, and we can write this more simply as the probability that y is less than or equal to B, but greater than or equal to A. This probability can be interpreted as the proportion of values in the population that are greater than or equal to A and less than or equal to B. So continuous probability distributions assign probabilities to intervals of numbers on the real number line. So if I know how a variable is distributed, I can use a continuous probability distribution to obtain the probability of observing a value greater than A but less than B. So again, continuous probability distributions assign probabilities to intervals of numbers on the real number line. So let's suppose that f of v is a continuous function of numbers on the real number line. So when I say function, it's just a formula, and for different distributions, we're often given this function. But suppose that f of v is a continuous function of numbers on the real number line. Consider the continuous curve that results when we graph this function. So let's say if we graph this function, we get something that looks kind of like this. As you can see, this variable is normally distributed. We can say that the curve f of v, so this curve is the continuous probability distribution of y, that the probability that y will be in the interval A to B is the area under the curve f of v corresponding to the interval A to B. So let's say that A is some value of the independent variable and B is another value. And this is a standardized metric of y, but I can look at the distribution of y or some standardized measure of y, call that v, and look at the continuous probability distribution, f of v, and I can use this continuous probability distribution of y if the probability that y will be in that interval A to B is the area under the curve, f of v, corresponding to this interval, so this area here. So the example that's in the notes is we've got a continuous probability curve f of v, and let's say that it represents the continuous probability distribution of the mileage of a randomly selected automobile. So we've got the continuous probability distribution of y. In this case, y is the mileage. The variable is the mileage of a randomly selected automobile. And suppose we wish to find the probability that y will be between 31 and 33 miles per gallon. So this might be 31 and this is 33. We can standardize these values, 31 and 33, using statistical processes that we'll cover in just a minute. And if we have some more information regarding how this variable is distributed, we can easily solve for the area under the curve in between A and B, or the probability of getting a mileage in between 31 and 33 inclusive. So if the curve f of v is the continuous probability distribution of y, then we say that the population of values from which y will be randomly selected is distributed according to the continuous probability curve f of v. So in other words, the population has the continuous probability distribution defined by f of v, and this height, the height of the curve. So if I look at the probability distribution of a variable, so if I look at the probability distribution of this variable v, and it could be mileages, there's some standardized mileages, and I know its distribution, and if I pick some value randomly, I'll just say v1, if I go up to the curve and then out to the vertical axis, I get the f of v1. So the height of this curve at any given point on the real line, which is the horizontal axis, represents the probability. It's really a relative probability that the value, that y, will be in a small interval of numbers around this point, v sub 1. So in other words, if this variable is mileages, and if I pick some value of mileages, I can solve for the relative probability by working off of this function that will be given. Of course, we can solve for these things automatically. It's very easy, especially these days using technology, but I just want you guys to know that there's a formula. F of v is a formula, so if I give you values of v, I can run them through this formula to give you the probability, the relative probability of observing a particular value of v. And I can use formulas to solve for not only the relative probability of observing a particular value of v, but the probability of observing a value that falls in the interval a to b. So I can get probabilities by looking at the area under the curve in between 2 points. So I can say, hey, listen, if you invest in this stock, there's a 47% chance you'll earn between 10 and 15%. Or I can say something like this: the relative probability that you'll earn 10% is equal to 0.001. If that makes sense. And again, this is a relative probability. You know that if v is continuously distributed, so it's measured on the real number line as a continuous variable, so it can be infinitely divided. The probability of any particular value is 0, so these are relative probabilities, but we can think of them as just probabilities. All right, so two properties satisfied by the continuous probability distribution are: 1, for any number v, f of v is going to be greater than or equal to 0. So basically what we're saying is that the probability is in between 0 and 1. Remember, the height of the curve represents a relative probability. And we can think of it just like some sort of a probability. And these probabilities have to be between 0 and 1. And then also the continuous area, or the total area under the continuous probability distribution. So the total area, this cross-hatched region, but the total area under a continuous probability curve is equal to 1. And this holds because the total area under f of v, this function, equals the probability that y will be between negative infinity and positive infinity. So I've got negative infinity here, and then positive infinity here. Actually, let me write those as negative infinity to positive infinity. So again, if we standardize the value of the variable under analysis, and if it's infinitely divisible, we've got an infinite number of values that v can take. And if we take the sum of all of these different values under the curve by solving for the area under the curve in between negative infinity and positive infinity, we get 1. I know that sounds a little too statistical, but this is stuff that you've probably seen before. To spend some time looking at the notes packets. And again, if you have any questions, feel free to call me anytime. But when we start to do examples, you'll see how easy this is. This is all a little bit too theoretical now, but when we start to work with specific probability distributions, like the normal probability distributions, we see formulas for the density functions, and we see how we can solve for the relative probabilities of particular values and the cumulative probabilities of intervals, things will start to make more sense. All right, so moving right along to the normal probability distribution. So we're going to discuss the normal probability distribution. This is also known as the bell curve. This is something that you've already read about. This is something that you've definitely seen working on your bachelor's degrees. So the normal probability distribution, many of the variables that we study in business are normally distributed. We saw an example earlier when we looked at the daily returns from investing in Microsoft stock. We saw that they were normally distributed about 0. So the normal